It's my great honor to have this opportunity to share with you some of my recent research. I will talk about from cooperative games to cooperative functions. I'm sure you are all very familiar with cooperative games. So what is cooperative function? I will elaborate this very soon. Let me just start here. Okay. We know that cooperative game theory is an essential part of game theory, and it has many important applications in management science, economics, computer science, biology, etc., etc. But one pity fact is that cooperative game theory is not appreciated so much by economists. Let me just give you two evidences. First, in the famous textbook by Foldenberg and Tirol, they didn't write any material about cooperative game theory at all. Second, for all the Nobel Prize winners in game theory, almost all of them win the prize for their contributions to non-cooperative game theory and its applications. For the 2012, for the 2012 one, when Shapley and Ross won the Nobel Prize, it's kind of special. Their many contributions, the market design theory, is neither non-cooperative game theory nor cooperative game theory. It's something in between. But anyway, until now, no game theorists to win the Nobel Prize for their contributions in cooperative game theory. So what happens? What's wrong with cooperative game theory? Because cooperative game theory has a very glorious history. For example, it's founding the book, the one by von Neumann and Morgenstern. Almost 2/3 of it was actually a cooperative game theory. So, and also many game theorists believe that cooperative game theory has its advantages. It is a higher level model. To use a cooperative game theory model, we don't need to know so many details as in non-cooperative game theory. So many game theories, including, for example, Eric Muskin, they believe that cooperative game theory may be revived in the future. And they list this as one of the most important open problems in game theory. So what's wrong with cooperative game theory? Here I list some of the major problems about it. Of course, it has some other problems. For example, as pointed out by Eric Muskin, in cooperative game theory, we usually assume that the grand collation always forms. And also, I'm happy to see that the talk of Professor Mazalov studies the cooperative game theory with partition forms. That is a very important topic. And also in cooperative game theory, we usually don't see the strategic behaviors of players. And here I list some technical ones. The first problem about cooperative game theory is that its basic setting as a set function. At the first sight, we may think that the set function is very simple, but actually it's highly combinatorial, highly discrete, and so it's not so easy to study a set function. For example, most economists master calculus, and calculus is the most powerful mathematical tool. It is a symbolic achievement of the modern mathematics, but usually it's very hard to use calculus in the study of cooperative game theory because that's a set function. And in accordance, usually we don't have close-formed solutions in cooperative game theory. Without a close-form solution, usually we can't see we can't see interesting management insights or economic insights besides the existence result. Of course, existence result is very important. Without existence, we can't see anything more. But without more managerial or economic implications, usually economists may not appreciate this kind of theory. And also, when the core is non-empty, it is usually very large, and we don't know which kind of core solution to use. And another problem is that in the serial cooperative games, we usually assume that players are able to sign a binding contract. So there will be a very powerful third party, for example, the government, to ensure that this contract can be implemented. And sometimes this is not very realistic. And also from a computational perspective, usually it's not easy to compute a core element. There are many NP hard problems, as also mentioned by Professor Mazalov. And also, suppose that we are given an allocation, and we want to know that whether this allocation is in the core or not. And even this membership testing problem is sometimes very hard. Let me begin with a very simple motivating example to show my basic idea of my framework. Suppose that there are two types of resources, capital denoted by x1 and labor denoted by x2, and the production function is CD1, such that the profit, the net profit, is simply x1 to the power of 1/4 and x2 to the power of 3/4. And suppose that there are only two players. Player 1 owns 4 units of labor, but no 4 units of capital, but no labor. And player 2 owns 4 units of labor, but no capital. We can see that no player can produce any profit alone. But if they cooperate with each other, then they can earn a net profit of 4 units. So the problem is how to allocate the total profit of 4. Let's look at the standard solution. In the standard approach to study this problem, first we transform this problem into a cooperative game, that is a set function. So the player set is 1, 2, and for player 1 and player 2 alone, they can't earn anything, and the worth of the grand collision is 4. This is a set function, and it's trivial that the core is fairly large. Any allocation, almost any allocation is in the core, so long as no one gets gets a negative profit. So the core tells us very little. So how about other solutions? For example, the Shapley value. We can see that the Shapley value suggests that the total profit of 4 is allocated equally between the two players. This seems very reasonable because the two players seems symmetric here. No one of them can earn anything alone, and by cooperating with each other, they earn a profit of 4. So this seems equally important. They depend on each other equally. This is the standard solution. Here is my not so standard solution. I argue that a more reasonable solution is that player 1 gets 1 unit and player 2 gets 3 units. Let's first have some feeling about this this new solution. First, it may seem not so reasonable as a symmetric solution because the set function is symmetric. So any solution concept that respects the symmetry axiom, including the Shapley value, will suggest that the reasonable solution is a symmetric one. So why do I suggest an asymmetric one? My main reason is that the original problem is not symmetric. Yeah, I agree that this set function is symmetric, but this set function is not our original problem. In our original problem, the two players are not symmetric because although player one and player two both own 4 units of some type of resource, but the two resources are not equally important. We can see from this CD function that the for capital X1, its power is 1/4, but for the labor X2, its power is 3/4. So we may feel that labor is more important than capital because player 2 owns all the labors. We may feel that it is reasonable to allocate more to the second player. So my new solution 1-3 respects this original asymmetry compared with the Shapley value. And how do I get this 1-3 solution? It is via shadow price 1/4, 3/4. That is, we imagine that the resources are sold at price 1/4, 3/4, and at this price vector, player one will be allocated 1 unit of profit, and player two will be allocated 3/4. And also this price vector 1/4, 3/4 mathematically is a gradient of this CD function at the point 4,4. And also it has another advantage, that is, suppose now we have 100 players and their initial endowment distribution is arbitrary, but the total endowment is still 4 units of capital and 4 units of labor. And in this much more complicated situation, if we use this shadow price vector to allocate the profit, then this allocation rule is still in the core of the new problem, and we can show that the price vector 1/4, 3/4 is the only one that satisfies this property. That is, no matter how many players there are, so long as their total endowment is 4,4, using this shadow price vector 1/4, 3/4, we can always get allocation in the core. In the core. And also we will show that 1/4, 3/4 is in the Walrasen equilibrium price vector. It is related with an exchange economy. So this is the motivating example. So we argue that for a large class of problems where there is an ordinary function like this CD function, the traditional way to study this problem is to transform it into a set function and use the cooperative game theory to study it. Sometimes we may use the Banarava-Shapley's theorem, for example. And we argue that this traditional way may not be so reasonable, because the ordinary function is easier to represent, it's easier to deal with, and in many cases we may use the calculus to study it. But the set function is much more complicated, and the calculus is not easy to use. And what's worse, during this transformation, some very important information may be lost. As in the motivating example, we may transform an asymmetric problem into a symmetric one. So why not deal with them directly? This is our basic idea, and in our working paper, we give a general framework for analyzing a class of problems that generalizes the motivating example, and we call these problems suppetitive market games. And for this class of games, we analyze them directly. The underlying ordinary function, and we call these ordinary functions cooperative functions, and we show that a variant of the call, we call it a variation call, fits this framework very well. It plays a comparable role as the call does in the cooperative game theory. And we also characterize several classes of this kind of functions, including the concave ones and the convex ones. And we provide several applications of this framework, including the Newswinder games, etc. This framework is a combination of several very old papers, including the famous paper by Shapley and Subic on market games. Here I study suppetitive market games. In that paper, they study concave. They study market games where the utility functions of the players are concave. But in my framework, I assume that this function is suppetitive. And another maybe not so famous one in the Society of Game Theory is also by Shapley and Subic, where they studied exchange economy and that economy is very convenient to use for TU games. And another paper maybe even fewer of us are familiar with is a JET paper by Shaki and Telsa. They study natural monopoly problems, but I feel that their framework and many of their mathematical results are very helpful for study cooperative game theory. Okay, so what is a cooperative function? It is an m-dimensional non-negative ordinary function which has a value of 0 at the origin, and this corresponds to our requirement that for a cooperative game theory, for a cooperative game we always assume that the worth at the empty value at the empty set is always 0, and we assume that this function w is super additive, and so it is when players cooperate, it is always the most efficient way for them to pool their resources together and produce in a collective way. And we also assume that there's at least one value x such that w is positive. This excludes the all zero function, which is quite interesting. So we may doubt that why bother to call a new term? Why not just to call it a production function or utility function? Because in many applications of this framework, this function may be sometimes a production function, and maybe sometimes a utility function, and sometimes it may be neither a utility function nor a production function. And also a very important point is that I would like to remind the reader that we assume that this function is always super additive. This assumption is not so usual. We know that in economics, in the general equilibrium theory, people usually assume that the utility function or the product function is concave. Although concave and concavity and superadditivity, they do not contradict each other, but we may feel that the overlap is not very large. So this is why I call it a new term. Okay, so what is a superadditive market game? This is a class of cooperative games I study. A superadditive market game is a triple Wn omega. Here n is a finite player set. Capital omega is the initial endowment distribution, such that each little omega j is the initial endowment of player j. And here this omega j is a vector of m dimensions, and w is just the cooperative function I introduced. And from this super additive market game, we can have a cooperative game very easily, because here W is super additive. So for each collision S, Vs is simply defined as W omega S, and omega S is to sum up all the omega J for players J in the collision S, because W is super additive. The most efficient way for them to cooperate is to pull their resources together. And of course, W is the essence of this problem. We call function W canned if the core. I use this to denote the core of the corresponding superadditive market game. If the core is non-empty for all player set and for all initial endowment distributions, that is, we fix W, but the player set N and omega may vary arbitrarily, and we would like to investigate this kind of function. That always derive non-empty calls for the cooperative for the corresponding cooperative game, and this kind of function corresponds to a balanced cooperative games or balanced set functions in the traditional cooperative game theory. And for this cooperative function, I define it's a solution concept called the variation call. This solution concept is defined for this function W at an arbitrary point x bar. Here we assume that each dimension of this S bar is positive. It is simply the set of shadow prices P, which has the same direction as the resources. First, we assume that the inner product between P and X bar equals W X bar. That is, all the profits should be allocated if we use this shadow price, and this corresponds to the core condition that the total profit is allocated to all players. And for each vector x that is between 0 and x bar, here for each dimension we require that this x is greater than 0 and smaller than the corresponding dimension of x bar. And for all of this x bar x, we require that its inner product is at least omega x, and this all corresponds to the definition of core that no collision of players have an incentive to deviate, because the total profit allocated to them in the allocation rule is greater than or equal to when they deviate. Note that here we got an infinite number of restrictions of inequalities. It is easy to show that the variation call is simply the price of the shadow prices, where each price vector solves an infinite many of problems. That is, as in my motivating example, so long as the total of the endowments sums up to is S bar, we use this shadow price vector to allocate the total profit. Then this allocation is always in the core of the original problem. So in this approach, a single solution, a single price vector solves an infinite number of problems in a unified way. Our first result is that W is canned if and only if its variation call is non-empty. One direction is very easy. If the variation call is non-empty, we can easily show that the W is can't because we can use the shadow price in the variation call to allocate the profit proportionally to their resources. But the other direction is not so obvious, but still the proof is not very difficult. So from this theorem, we can feel that the variation call plays a comparable role as the call does for cooperative game theory. And the intuition for the proof is that in the definition of the call, there's a finite number of restrictions, but for the definition of variation call, there are an infinite number of restrictions. But when we consider all competitive market games, that is the player set N and the initial endowment omega varies arbitrarily, and when we consider this, the effect of the difference between a finite number of restrictions and an infinite number of restrictions vanishes. There are some similar results in the literature. For example, in the Shaki and Tulsa JET paper, they also have a similar result, but in that paper, the call is defined not in our traditional way. And also, Olsen uses the in a recent working paper uses the traditional call to define a similar to characterize this problem, but their basic assumption about this class of functions is not super additive. Instead, they assume that the function is super homogeneous. That is when homogeneous means that f lambda x equals lambda fx. Super homogeneous is defined such that f lambda x is greater than or equal to lambda fx. This definition of super homogeneous. So our starting point is quite different, and also my proof is completely different with both of them. Sorry. Okay. You may you may ask, why do I call this solution concept the variation call? Because variation is a big name, and we know variation equilibrium. I have good reasons, because this corresponds to a variation equilibrium price set in a properly defined exchange economy. Here we view this competitive market game as an exchange economy, such that all players have utility functions W, and allocation omega star associated with the price vector P is called variation equilibrium. If it satisfies this optimality condition, that is, each player considers how much resource to consume given the price P to maximize its quasi-linear utility function, and he or she may find that this omega J star is his optimal consuming quantity in so long as the domain of this optimization is that it is non-negative and it does not exceed the total endowment of the whole society. And also we have this market clear condition. Oh. Sorry. This exchange economy and variance equilibrium is defined by Shapley and Subic in the 1966 paper. I would like to remind you that this exchange economy is not the standard one we learn from advanced macroeconomics, because here we have no budget constraint, and also equivalently we assume that each consumer possesses a sufficiently large amount of money, although this is not explicitly written in the definition. And also we have an additional constraint, that is the optimization is done over this domain, and in the standard exchange economy and the standard variance equilibrium, we don't have this restriction. And my second result is that the variance equilibrium plus vector set, that is, we put all the variance equilibrium plus vectors into this set, and we find that this set is precisely the variance core, and this connects the core allocation to a market, and we may use this market or some kind of pseudo market to allocate the profit distributionally or decentralized in a decentralized way, and this also further justifies the importance of variance core. And I would like to remind you that there are many similar results in economics or in the general equilibrium theory, where these results are called the core equivalence theorems. But this result is different from any of them. I will move to the details. I also define relaxed variance core. This can be viewed as some kind of anomalized the set of anomalized price vectors, and technically this relaxed variance core may be much easier to analyze, and also in some sense it is equivalent to the variance core. We can get the other, we can derive each other very easily in this formula. Using this term, we can give another characterization of the kindness of a cooperative function. That is, a cooperative function W is kind if and only if there's a vector P such that this function W grows faster than the linear function determined by the vector P. That is, for all x that is smaller than x bar, the ratio that wx bar divided by wx is greater than or equal to by the inner product between p and x bar divided by the inner product between p and x. We can view this as the corresponding ratio at a linear production. This is also intuitive, because to guarantee that the profit can be allocated such that all players, all groups of players are satisfied only if we earn a lot, we earn sufficiently large profits. So this function W should grow relatively fast. And also we can show that when this function has only one dimension, W is a one-dimension function, it is kind only if and only if Wx divided by x is weakly increasing. So this is very neat, and we may feel that this is just another version of convexity. But let me show you that this is weaker than convexity. For a one-dimensional function, if it is convex, then it must be a kind. But a kind one-dimensional function may not be convex. And also we can show that when W is differentiable, then the gradient may play a very important role, as I show in the motivating example. First, if W is kind, we always have that its gradient at the origin is upper bounded by its gradient at the x bar. And also, its Walrancian call is always contained in this interval. One part of this proposition that is the Walrancian the Walrancian call is always upper bounded by the gradient of this function at the x bar. It is have some similar results in the standard cooperative game theory, where we know that for any call allocation, each player's profit is at most its marginal contribution to the grand collision. Here, x bar corresponds to the grand collision, and its gradient corresponds to the marginal contribution to the grand collision. So this property have a nice similar result in the cooperative game theory. And we also show that when W is continuously differentiable and also strongly homostatic, then its gradient is always in its relaxed Walrancian call. So for this kind of functions, its gradient is always useful. So what is strongly homostatic? For homostatic, it means that it is a monotonic transformation of a homogeneous function, and strongly homostatic. By strongly homostatic, we require that it is an elastic transformation of a homogeneous function. And also, if W is homogeneous of degree D and D is greater than or equal to 1, then we have this first order condition. And this condition is much easier to check. And you may wonder that whether this kind of function is popular or not. Can we give some examples? It turns out there are lots of this kind of functions. It's quite popular, and many functions that are frequently used in economics, in management science, are actually kind cooperative functions. For example, a quadratic function is kind if and only if all its coefficients are non-negative. And from this, we can see that this class of function is quite different with convex or concave ones, because here we do not require any condition on this matrix, on this coefficient matrix, whether it is a positive definite or negative definite. We do not have that kind of requirement. We will show that this class of functions has a non-trivial intersection with both concave functions and convex functions. And also this for many CD production functions, as I mentioned in the motivating example, they are kind, and also many CES functions that are commonly used in economics are also kind. Next, I will show you a characterization of this class of functions when we require that it is concave. And that is, we study concave cooperative functions. It turns out that a concave cooperative function is kind if and only if it is homogeneous. And in this case, the Walrancian call is always a superdifferential of this function W at the point x bar. And the superdifferential is a standard concept in convex analysis. And also, in addition, if W is differentiable, then from standard convex analysis, we know that its superdifferential has a single single point that is gradient at this point. And here we have the variation call has a single point. You may wonder that this class of functions, concave and also supputative and also homogeneous, it may be a very narrow class of functions. In some sense, you are right. Yeah, it is. This class of functions are quite narrow, but in some other sense, we can show that this set of functions is wide enough. It is very useful. So what do I mean by this? We can show that a cooperative game is totally balanced if and only if it can be represented as a supputative market game with a cooperative function that belongs to this class. It is concave, it is supputative, and it is homogeneous. So if we would like to study totally balanced games, our framework is interesting enough to include all of them, to represent all of them. And if you are familiar with the result of the market games by Shapley and Subic, you will know that this is an analogous result, and the proof is quite similar. And also, I study convex cooperative games. That is one cooperative game that is we study when the convex cooperative game is kind. This problem has been studied by Shaki and Telsa and also by other scholars without using our term. And it is known that supputative convex function may not be kind. We may feel that this is strong enough. Supputativity means economy of scale, and convexity means that we have increasing returns to scale, and for this kind of functions, they may grow fast enough to guarantee that the call is always non-empty. But unfortunately, this is not strong enough, and this shows that additional necessary and sufficient condition is supermassive modularity. Here we provide a weaker condition, but this condition is still seems quite complicated, and I will skip the details due to time constraint. And also, we have a second part result. Our theorem consists of two parts. First, we show that a convex cooperative function W is kind if and only if it satisfies some additional condition which is weaker than supermodularity. And also we show that its variation call at x bar is in some sense equivalent to the ordinary call of a special superadditive market game. And this second part of this second part result has actually appeared in Shapley and Subic in their 1975 paper, where they wrote that their method of analysis depends heavily on the assumption of concave utility functions. But here we see that it also works for convex functions, and we will see that actually convexity or concavity does not matter. They are not the essence of this problem. And also for this additional condition, it is very simple when the dimension is low. That is when m is at most 2, then it is automatically satisfied. And when m is 3, this additional condition is explicitly written here. And also, if the m is 2, we can give an closed form solution for the virus and call. And okay, how much time do I have? 6 minutes.
Hello. Yes, actually, your time was up maybe 5 minutes ago. Of course, we have started a little bit later, but I think this is. If you want to summarize some most important things, we would be very happy to listen. Maybe.
Okay. Okay, I will use this remaining 5 minutes to introduce another result. In the above I have studied the functions that always derive non-empty calls, or always derive balanced cooperative games. Here, I require a little bit more. I require that the function always derive convex games. We know that convex games have some further nice properties compared with ordinary balanced games. We find that this class of function can also be characterized cleanly, which it turns out that this kind of function is the ones that is coordinate-wise convex and supermodular. And also this function is this class of functions is relatively new in the literature, and a comprehensive study of this class of function is by 2005 MOR paper. I will omit the applications of this framework. Okay, let me use 2 minutes to summarize. In this talk, I introduce a general framework for analyzing a class of competitive market games. And it turns out that this class of problem is wide enough in the sense that any totally balanced game can be represented as it. And we show that for this class of problems, because there's an ordinary function analyzing it, so we analyze this function directly instead of transforming it into a set function. And we find that the virus and call plays a very critical role in this framework. And we also characterize concave cooperative functions and convex ones. And one major restriction of this framework is that here we assume that resources are additive. In many applications, the resources may not be additive, and for that kind of scenarios, we may need to explore more about this theory. And this is all. Thank you. Thank you.
Okay, thank you very much. So if there are no questions, I want to ask for the next presentation that maybe we have 15 minutes for the presentation, 5 minutes for the questions, because we already 20 minutes later for the schedule. Thank you once again for the great
Thank you.
plenary talk. Just a few questions. I can see that you are interested in the axiomatic game theory, in axiomatic cooperative game theory. I have a question whether you are interested in the dynamic setting, and have you considered the time consistency property as an axiom for the cooperative solution? Because in St. Petersburg, one of the most important directions are the dynamic cooperative games, and time consistency is a kind of our favorite axiom and the property.
Yeah, of course, we all know this. So thank you. This is a very good question. We know that the dynamic cooperative game theory is a very important branch, and for most of the applications in the real world, the problem is dynamic instead of static, and there are lots of important problems to study in this branch. Unfortunately, for this, for my work, because it's very preliminary, so I only considered the static or the one-shot problem instead of the dynamic ones. And maybe in the future, I will consider the dynamic version of it, and we'll study the interesting time consistency problems. Thank you.
Thank you very much. If you're interested, we would be, at least I would be very happy to exchange some papers and send you a paper about the IDB core. This is a kind of solution that is constructing using the axiomatic approach, as in classical cooperative game theory, axiomatic approach. But for dynamic setting, and if you're interested, if you can send some
of course
related papers, I would be very happy. Thank you very much. Anyone has any questions?
Thank you.
Anyone has any questions?
Avanes, can I ask?
Yes.
Yeah.
I'd like to ask you about the parameters omega j that is included to Wallerasian equilibrium and the Wallerasian core, and what about strategy proofness? So if we change omega, what it will be?
Oh, thank you. This is an excellent question. A very excellent point. Here we assume that all players report their parameters omega j truthfully. We didn't consider any strategic problem, and maybe in the future we will consider that the truthfulness problem, because that's a very important dimension. Thank you for pointing this out.